When the Earth ruptures beneath a populated grid, the damage is absolute. Brick facades are sheared off, load-bearing walls buckle, and entire structures are reduced to fractured concrete and exposed rebar. The ground during one of these events does not shake with a clean, repeating rhythm. It delivers a jagged, erratic, time-varying load that jerks back and forth with zero predictability. For a structural engineer, looking at a blueprint and simply guessing how thousands of tons of steel will react to that specific sequence of random jolts is not an option. To design a building that stays upright, you need a mathematical bridge between input motion, the chaotic forcing from the ground, and response, which is what the steel actually does. Developing this mathematical bridge is what allows engineers to move from observing past failures to simulating how a specific design will withstand a future disaster. To understand a 5-minute earthquake, we first chop that massive continuous wave of energy down into individual momentary fractions of a second. Think of it like the mechanical logic of an arcade game. We are ignoring the entire complex level for a moment to isolate one single discrete tap of a button. We hit the digital model of our building with just one of those isolated taps to find its unit impulse response. The unit impulse response is the specific, measurable way a physical system wobbles and then settling down when struck by a single instantaneous unit of force. Once you map out how the structure rings like a bell from that solitary hit, you possess the baseline reaction. You know the exact mathematical shape of the building's natural sway. Figuring out that isolated reaction is the required first step. It gives you the blueprint for how the structure absorbs and dissipates energy from any future vibration. But an earthquake delivers thousands of those hits back to back, often violently reversing direction before the building has time to recover from the first strike. This animated diagram plots how we handle that continuous barrage. As each new hit drops onto the timeline, we use convolution to multiply it by the building's unit impulse response. Convolution is a mathematical operation that expresses how the shape of one function is modified by another, effectively letting us apply the building's known wobble to every single incoming tap. Then superposition takes over. Superposition is the physical principle stating that the total response caused by multiple overlapping forces is simply the sum of the responses caused by each force individually. As the scanner sweeps across the timeline, it mathematically stacks all those overlapping decaying waves together, summing them into one final chaotic output wave. In structural mechanics, engineers call this specific time-based stacking process Duhamel's integral. Duhamel's integral calculates the exact physical strain of vibrating structure experiences as an external load changes second by second. If you look at general physics textbooks, you'll see this identical relationship, where the total response equals the initial forcing multiplied by the system's inherent properties, written as Green's functions. Green's functions are mathematical tools used to solve complex differential equations by calculating the response to a basic point source first. The labels on the chalkboard change depending on the physics class, but the engine churning through the variables to calculate cumulative damage is always convolution. There is a computational roadblock, though. Manually calculating thousands of overlapping wave decays second by second in the standard time domain is mathematically exhausting. This animated visualization shows the engineering shortcut. The complex timeline of overlapping waves morphs into the frequency domain. The frequency domain, or transform space, is a way of analyzing mathematical functions, not by how they change over time, but by isolating the specific frequencies, or pitches, they contain. By translating the earthquake and the building into this transform space, the grueling calculus of convolution in time becomes basic multiplication. You simply multiply the ground's input frequencies by the building's frequency responses. Top engineering programs teach this frequency-based multiplication as the foundation for transfer functions. A transfer function is a mathematical formula that models a system's output for each possible input, and MIT's systems notes use this exact transform logic to solve complex structural problems, like how layered soil amplifies seismic waves. If you encounter Green's functions, Duhamel's integral, or transfer functions without understanding the connective tissue, they feel like isolated math tricks to memorize for a test. Convolution provides the unifying logic for these diverse tools. It links the response of a single point to the behavior of the entire system under any general load. By breaking chaotic violence down into single impulses and stacking them mathematically, engineers map out exactly which structures will stand firm and which will fall.